Hello, I'm going to talk today about verified Debian packaging at scale. This talks about a project that we did at Cloudflare to help improve our security. So before I get started, I'd love to ask a little question here just to get some audience participation. How many people here use Debian or a Debian-based Linux distribution? Let's see a raise of hands. Ooh, that's awesome. What about like RPM or Red Hat based? Cool, multiple hands, same hand going up. We got Arch users? We got one Arch user, awesome. Kudos to you. Any Gen 2 Linux from scratch? Okay, anyway, don't worry about it. Like this talk, it has verified Debian packaging at scale in the name, but like the kinds of things that we're talking about should be fundamental to anybody using Linux or doing things. We're going to talk kind of at the fundamental level, not just about Debian, but Debian's part of the story. Okay, so our goal here is to share some of the knowledge that we gained while doing this project, and we're looking for feedback. So folks might say, hey, that was cool that you did it this way, but did you know about this other thing? And I think that's what's really cool about these sorts of conferences is learning from each other. All right, so first of all, we'll start off with who are we? Who am I? I'm Chris Arges. I'm a senior systems engineer at Cloudflare. I've worked across the Linux ecosystem for my entire career, from bring up kernels on new hardware to deploying things at scale. And my interests are coaching, so I actually coach kids soccer and kids robotics teams, and teaching kids Python is awesome. I play with modular synths for fun, don't really have a lot of time for that, and then I also run. So those are my interests. And we also have Fred.
Hi, my name is Fred Lawler. This is my third time speaking at Texas Linux Fest. Second time today, third time total. I didn't make this slide, so I just looking here a little bit. Apparently I like kayaking and cats, but my primary role at Cloudflare is security, and I work with Chris, and I also dabble with Linux security modules.
Cool, thanks Fred. Awesome, so let's get started and talk about Cloudflare's global network. So one thing that not a lot of folks realize, but Cloudflare, we actually physically install and run our own servers in data centers all across the world. So we're not running on other people's clouds, we are our own cloud. And what this means is we actually have to handle the entire server lifecycle, from racking the machines, renting space, doing all the physical things, plugging cables in, and then actually imaging and installing Linux and managing software on those systems. Our network is pretty massive, so all these little blue dots here show you cities that we have data centers in. So we have data centers in over 330 cities. I had to actually update this slide before release because this number increased. So 330 cities across the world. Each city can have multiple data centers, one or more data centers, and we have large numbers of servers there. We also operate an anycast network. What this means is if you try to access a Cloudflare IP, you don't just go to a specific server in New Zealand or something like that. It actually just goes to the closest server. So we optimize our infrastructure for low latency. And what's cool about this is it makes it a very large distributed system. And this is one of our superpowers. So it has incredible redundancy when you work with our servers across our edge network. But it also is a challenge. So as a software developer, as a systems developer and engineer, we have to make our stuff work everywhere, all the time. Okay, so let me talk a little bit about Cloudflare software stack. We use rock-solid Debian Linux. That's what we build that's our distribution that we use here at Cloudflare. We also build, run, and continuously upgrade our own Linux kernel based on stable. And if you got to see Ignat's presentation, he went into more detail about that. So when folks at Cloudflare want to ship software, they use Debian packages. So they actually have to build a Debian package, and then we get to ship it across all of our servers, not simultaneously. I'll talk about that. And developers can also use containers. Developers can also just apt-get install a Debian package out of a Debian repository too, so we leverage standard stuff as well. Okay, we orchestrate all this stuff with Salt, and this allows us to have this infrastructure as code approach to how we distribute and do things. So some of our philosophies in summary is, another thing I mentioned is that actually every server is running essentially the same software. So we don't have special server A over here and B over here. They're all capable of handling traffic for any service. And this is part of the Anycast implication we have with how our stuff is designed. We also don't have fixed release schedules. So we release all the time at any time. Whenever somebody on a team decides, hey, be a good day for a release, it's Friday at 5 p.m. somewhere, that release is going out. And we have to handle that sort of thing. And then finally, when we do deploy, it's not just like push button, deploy everywhere, developer goes to launch. No. We deploy very slowly and carefully into subsets of data centers, look at health metrics, look at lots of Prometheus things, and then go to the next thing. So we're trying to be careful. We don't deploy everywhere at once. Okay, so let me talk about like where did our project, what was the reason for this project? And the reason for this project that we're going to talk about is an incident that we had in Thanksgiving of 2023. So we detected a threat actor that had infiltrated our internal systems. Some forensic analysis revealed that this actor was able to pivot into our self-hosted Atlassian servers, and this is running our Jira and Confluence instances. So they're able to access source code and as well as wikis and things like that. So of course we took this incident extremely seriously, and we created this initiative called Code Red. Here's an example of a different kind of Code Red. Maybe it helped us solve some of the security things. But this company-wide initiative, the goal of us was to improve our security by dedicating large portions of engineering and security folks to doing so. So for more detail, if you're curious about what actually happened at Cloudflare, like one of our principles is being sharing and being transparent. We have a whole write-up on our blog, and you can scan the QR code or type that URL into a browser and read that later. We're not going to talk about that. We'll talk about the security stuff that we did. All right, so our goal with our initiative was, one, to improve depth of our security all across all of our systems. But one thing that we thought about was, can we actually trust the software that's actually running on our servers? So we're all over the world, there's binaries running, but do we know? Is that the binary it says it is? So we focused on that specific goal, which was preventing attackers from running arbitrary scripts or programs on our servers. So what actually do we mean by arbitrary scripts or programs? Essentially, it's anything that can produce machine code for the CPU to execute. So I got a little obj dump output here for folks who like that sort of thing, just to show you like this is some code that can execute on a CPU. And so this includes a couple of different types of things. So one we might think of is, you compiled something with GCC and you have an a.out elf executable. Yes, we want to make sure we know that those things are. But also there's other things like object code files that can be memory mapped into your program and executed, or shared libraries. So think like, if you ever heard of an LD preload type of an attack, yeah, like we want to make sure that code's also good. Another set of things that we need to actually verify are scripts. So if you're familiar with the execve syscall, so when Linux actually executes not only binaries but also scripts, it goes through a syscall, and Linux looks at that first little line, that shebang line, and says, okay, what interpreter do I need to load? And it executes that. So that's also a vector for attack that we want to be really careful about. So our goal is to verify everywhere at this fundamental layer of, if it can execute, we should be verifying that executable thing. All right, so just summarize some of the requirements. Like I mentioned, our systems are very dynamic, so we don't have immutable operating systems. We have very dynamic systems, like packages can be installed, updated, removed at any time. When we deployed our solution, we didn't want to break other developers' solutions. So we can't tell, hey, the whole company, please stop developing code and product to satisfy this initiative. We actually needed to work with other teams' workflows. The verification that we did needed to be done before any code was executed. So this is really important. We can't just deploy everything and then later check it and say, yeah, it looks okay, I'll check it in another couple hours. It needed to be done at time of execution. And of course, developing any sort of trusted or signing process needs to be incredibly secure, because if you do, you spend millions of dollars on crypto and somebody comes by with the $5 wrench and injects, their own signature earlier in the process, like that whole thing was for naught. So we want to make sure that signing happens in a trusted location, and then anything we do with private keys or any sort of secrets need to be not exposed to the rest of the company or really anywhere it doesn't need to be exposed. And like I mentioned, we have to do this for anything that can execute. So when we do this project, of course, like any project, you want to look at what exists today and what can we actually use off the shelf. And one of the things, if you're familiar with Debian packaging, is, hey, archives have GPG signatures on them. We have a way to verify that that package that I downloaded from that repository, there's a signature on it and there's a hash and a signed hash of that thing. And that's awesome. And this actually verifies the package is what it says it is when we apt installed it, or apt get it from the remote repository. The problem is, if somebody just sideloads it, or like dpackage-i installs it, it doesn't do that verification. So it's really easy to bypass. There's also some interesting extensions in Debian packaging where you can actually inject a signature into the package. And this is great. This solves that dpackage-i problem. But again, the other problem here is, well, somebody could just, maybe write over your binary with their own kind of malicious code. So really, we needed something that really verified more at that kernel layer rather than just trying to do this at kind of a pure like packaging user space layer. So I'm going to turn over to Fred. He's going to talk more in depth about how Linux actually helped us verify the binaries.
Thank you, Chris. Now for everyone's favorite time in the presentation, when Fred gets to talk. Cool. Okay. So this really lends itself nicely to what are known as Linux security modules. So if you guys are not familiar, Linux provides various tools such as AppArmor, BPF, Lockdown, SELinux, etc., to essentially control access to certain files or maybe capabilities or maybe system resources, like in the case of Lockdown, or have dynamic policy in the case of BPF in order to prevent malicious actors from accessing, leveraging certain files and things on your computer. However, we are actually interested in integrity. So another LSM that was introduced is called IMA, Integrity Measurement Architecture. And what separates this from the other LSMs, and I'm pretty sure there's one on SELinux after this one in some other room somewhere, but the thing that differentiates this from the others is that IMA actually targets the mutability of files and memory. So we can use this to ensure integrity on these files, and when we execute them, we know that they are what they say they are. And the nice thing about this is if you have a TPM on your motherboard, IMA also writes a log that's, it's an attestation log that's backed by the TPM. So you can actually prove that what you're verifying and looking at is actually what you think it is as well. It also has some other benefits. It's commonly used for kexec, so you can sign your kernels, and when you kexec into them, you know that those are trusted. It also supports modules. It can be a drop-in replacement for current kernel module signatures, and is also supported for Secure Boot 2. And the way this works is that IMA will compare hashes and verify integrity. But before we get to that, we need to understand how they're stored. So IMA stores these hashes in what's called extended attributes, and in particular, security.ima attributes. So you store your hash in this part of your file system attached to your file, and then IMA uses that to compare against the hash of the binary that you're trying to execute, and we'll touch up on that a little bit later. But essentially, you know when a file system has these capabilities if you look at the superblock struct within this kernel source code. This is where you know which file systems have this support, and the common ones I put up here are BetterFS, exe, OverlayFS, XFS, and etc. But these are all registered at time of module init. So whenever you load up your module, your file system module, that's when these attributes can then be used to store and retrieve the hash. So let's talk a little bit more about the verification. So IMA does verification in essentially two ways, but before you do any verification, you actually have to have the hashes in the first place. So what you're supposed to do with IMA is you're supposed to take your node, reboot it, and apply this ima_praise boot parameter and put it into something called fix mode. So fix mode will allow you to open up all your files on the file system before you get into your user space. And what it does is it hashes every single file, stores that hash in the extended attribute, and then you have two options afterwards. You either reboot into log mode or you reboot into enforce mode. Log mode is exactly as the name implies. It's just mainly used to show that these files are being accessed, that you can read your attestation log and say like, oh, this file is verified, etc. And obviously enforcement does that, but also throws an EPERM denied error if you try to access these, or try to execute and access these files. So let's look at enforcement in more detail. So, as I alluded to, the way this works is that generally speaking, not all file systems implement it this way, but generally speaking, when your inode has an update, and what I mean by update, some change happened to your file, the inode version gets updated, and then the kernel will try to hash it, and then praise it, and then log it in the attestation log. But in between then and there, we also verify if this file is what we think it is. And if it is, we go ahead and we let the user execute it. And if not, we throw that EPERM error. And then we also log that in audit log or something similar that this file was denied execution. But the cool thing is this is all cached. So worry not, whenever you execute your binaries, it's not all going to try to hash it every single time. This really lends itself nicely to immutable OS. So there's been a lot of talks today about immutable OS, but you know, us being Cloudflare and Chris made a fine point of this this morning. We are this afternoon, we are extremely dynamic, and this whole flow of reboots doesn't really work for us. Plus, you can imagine in cases of incidents, you don't really want to have to reboot your node 2 times to get anything done. It's just kind of wasteful. Good news is IMA has support signatures. So basically what this means is we can actually generate signed hashes at a later time or an earlier time and then apply them later. So essentially the way this works is you have some sort of public or private key pair. You take the hash sum of the file you're trying to verify later, and you sign it, and you get what's called a signature, and then later you verify that signature, and then you compare the hashes, make sure everything's A-OK. But this lends us to the next question. Where do you actually store this key at, right? And it's really good to kind of take a look at this from a module verification perspective, because the way module signatures work in the kernel, you generally generate some sort of private key, you sign your module, and then you put your certificate that contains a public key to verify it in something called a system trusted key ring. And a system trusted key ring is essentially a global key ring where you can store all your favorite public keys to verify whatever you want. But there is a problem with that. Recall earlier I said that IMA is good for modules, but we're trying to sign binaries. So what does this mean? If we try to sign binaries with a private key, this means this private key can also be used to sign modules. We don't want that. We actually want to decouple module signing from binary signing such that we can take our module key, throw it away, and we don't have to worry about binaries that are being signed somewhere else. We don't have to worry about that key being leaked, signed kernel modules, and loaded in at runtime. So we came up with something like this, where we take the public and private key, and those are stored off in some key management storage area, and we take the public key to generate some sort of certificate that we then use the ephemeral key that we use to sign our modules to then sign that, and now this gives us the ability to insert the certificate that verifies binaries at runtime into what's called the IMA trusted key ring, which is verified by the system trusted key ring. So now we have modules that are verified by the system key ring, and we also have this certificate that's trusted, and that truly decouples this. But you're thinking, okay, Fred, well, we did IMA, IMA supports modules, so you have to do something to kind of still break this apart. And yes, there is a config option in the kernel called ima_praise mod sig, and we have to set that to no in order to have this truly decoupled change. But with signing out of the way, we have to distribute these somehow, and logistics is very hard. So, Cloudflare, we have a couple ways of building our file systems. The main one being we have a base, what we call a base image, or you guys may be familiar with as an InitRamFS or an initRD. And this is what we use when we boot up our nodes. The problem is that these archive formats, if you're not familiar, when you create a root file system, you generally archive it and compress it and then load it in later at the kernel at a later time. Which contains all the necessary binaries to then like perform the next level of boot in the init to get you to systemd and then get you into user space and do your root switching and things like that. But the problem is that these archive formats do not support extended attributes. So if we store our hashes inside of these attributes, this is kind of a problem, right? Like we need to be able to verify our initramfs at boot time. Someone in the kernel community thought of the same thing, so they invented this thing called newcx, and it was not merge. We also looked at a different approach using elf sign that kind of operates similar to module signing, such that signatures are tagged onto the end of binaries and then verified that way. But then you got another problem. What do you do with scripts, right? Because they're mostly plain text. So, and because we mostly use Debian packages, why don't we just ship this stuff with Debian packages? And the anatomy of a Debian package is essentially this. You have some sort of binary blob that gives you the, it's ASCII of course, but it's some file that, that tells you that this is indeed a Debian package, and you have two special archive packages following. We have a control archive package, and you have your data. Control, where is all of your pre and post install scripts exist, and the data is where all of your actual files, man pages, binaries, whatever, is all exist in that archive package. So what tools can we use to sign these things? So by default, Debian, and I guess you boot to another, I should just say that I'm a maintainers, ship this tool called EVMCTL, which allows you to sign these packages and it generates the signatures. But because we're dealing with Debian packages, we want to make this kind of like optimized as possible. So we invented our own tool that is in charge of unpacking, signing, and then distributing these extended attributes. And this tool is very tuned to be very performant. And I think Chris has some metrics to go along with that. Okay, cool. So with all that taken care of, how do we ship these, right? So this was actually a major problem because when we think about how to actually ship this, there's a few approaches that we can take. Traditionally, with debug symbols for your binaries, you kind of create two different packages and you submit them up to like maybe two different repositories or something like that. And then tools like GDB or debug infog can download those debug symbols, and then you'll have access to those debug symbols when you actually need them. The problem is that with an approach like that, especially with something like with debug infod, you might need like extra infrastructure that introduces extra cost. How do you keep this up to date? Yada, yada, yada. And same thing with the global manifest file, which essentially being we have this file that exists on our computer, or we have this file that exists as one Debian package. How do we actually update this constantly, right, and not step on each other's toes at the same time? But the good news is if I recall correctly, there is work being done in the kernel to kind of bring this global manifest file into the kernel itself, to where you can then put the extended attributes into the kernel and cache it that way. But I haven't been following too closely, so I'm not entirely sure if that's been merged in the latest release. So instead, we took a different approach where we are going to now put the manifest file. We're going to still use that approach, but we're going to put that manifest file into our actual Debian package and then ship our Debian packages that way. And we have two links here. Debian, you'd think by default would have a mechanism for this. They do not. There's a link there to where there's an ongoing discussion on how to best create these manifest files for Debian. The next link below that is an earlier implementation from IBM, where they attempted to actually bake in support for extended attributes into Debian. So with the manifest file decided, we needed to format it as well. Sorry. So we decided to go with the traditional format provided by libattr, which is provided by the attr package. This format is pretty simple. It just has a file line with a path, and you give the extended attribute with its data, and that's the end of it. We decided to go with this approach because it already exists. It allows you to use your own tools or use other tools that kind of control extended attributes. There's even an Etsy file somewhere that lets you control some additional security around them. So we want this approach to be a little bit more scalable, and that's kind of like where we went with that. But we still need to distribute the manifest files somehow. So we kind of looked at two different approaches with this. We were also, with the alluding back to the debug symbol approach, we're thinking about installing these in a different part of the file system, similar to how you would install the debug symbols, like in some /lib debug build something folder. But we actually ultimately ended up putting this into the control file, so that way when you install these Debian packages, the extended attributes file always exists in this one specific spot that's easy to get to, easy to apply to the files when it comes time to apply those. Speaking of which, shipping is one thing, applying is another. So this was kind of fun, actually. This is where the project really became fun, because there's several ways to actually apply these. One of the main things we looked at was triggers, and we had some success with this. But the problem with triggers is, if you're not familiar, whenever you install a package, you could bake in some additional functionality that triggers after you've installed it or during installation. But the problem is we need to actually handle the post and pre-install scripts for packages. The funny thing being, those actually install in a different location from where they're actually executed, which means that we have to know the file path ahead of time to actually apply the extended attributes to those files before they're being executed. So we looked at hijacking tar. So the way this works is we noticed that through running strace on dpkg-install or something like that, that there's dpkg will actually exec into tar to actually extract files. So if you theoretically have a symlink in there that's your own tar program, you could hijack that, go into, and then when the program, and when the extraction happens, go ahead and then apply the extended attributes then. But the funny thing is that Debian actually doesn't work that way. It actually uses tar only to extract the pre and post install scripts, and has its own implementation of extracting data files from the data.tar outside of that. So which means hijacking tar doesn't really work, and we actually ended up having to patch dbkg itself. And we did this by introducing a new post invoke hook. So there's already one for install, but the problem with install is it only occurs after the entire state machine has happened. So what I mean is you execute dbkg-i, you install your package, but at the very end does your post invoke post installs hook come into play. But we needed something in between that state, right? Because we're trying to get the execution of the pre and post install scripts and the actual binaries as well. So we invented this little hook to hook in there to do just that. But this also means we need a new tool. So the way if you recall earlier from initram FS, we couldn't really store the extended attributes into the binaries themselves because the archive format doesn't support it. But the nice thing about storing it inside of the control part of the tar file is that now these extended attribute files exist on the file system at init time. So this custom tool can now at init time, at boot init time, take those extended attribute files, apply them to the entire file system before they're executed, before user space, and then after user space has already come into play and we start installing packages. Now, when those packages install, we can then do the normal data tars, or we can do the normal post unpack and invoke script hook as well at that time. So we then have extended attributes when we're ready to execute our programs. But the interesting thing here is that this kind of introduces a little bit of a problem security-wise. Now, it does kind of introduce a little bit of a DOS situation where an attacker can kind of get in between this place and prevent us from executing code even further. But I mean, you know, as they say, security is Swiss cheese, right? Like you have several layers of security to kind of combat that problem. But in order to do all of this in the first place in the boot init process, you need to make sure to tell IMA not to enforce the security before you apply the security attributes with the IMA appraise build policy config option. Set that to no, and then all of a sudden you're able to actually execute your code. And you know, this is what it looks like in a nutshell, right? So there's a lot of information here, but it can really be summed up into this image, right? So we have a CI build process that relies on this package signer that contains the extended attribute contract, meaning the libattr file format. This has a dependency on our KMS where we actually store the key again. And then on the flip side, when we actually go to the distribution at boot init, we have our initRemFS, which contains our policy for IMA and our certificate for IMA. And then the boot will also use the same dpkg utils package that we built and supply to then apply the extended attributes at boot time, as well as when the apt installer dbkg install time happens too, so that way we have everything signed and ready to go before execution. XATTR is applied before execution, so that way when we execute, we're good. And with that, I'm going to hand it back over to Chris to show how we got this into production.
All right. Thanks, Fred. Cool. So Fred explained how we could get things working end-to-end and really the details of what we needed to do. So the next logical question is like, yeah, let's get this working all across our production environment. So the first thing we started with, of course, is the plan. So we put together a plan where we knew we had to deploy some modified packages, like Fred mentioned, and different tooling into our infrastructure. We wanted to sign all of our base images and ensure those were deployed. After that was done, then we could work on first-party packages, and this being like things in our own CI system. And basically what Fred described in that end-to-end diagram was that approach that we took for that. After that's done, then we actually want to sign all upstream Debian packages. And what I mean by this is because developers can apt install any package, we needed to make sure that they were all signed. Another deployment mechanism we had were our container images. And so that the binaries inside those images also needed to be signed. Finally, when we get to this point, there's always one-off executables and scripts. So we use Salt to render things on our edge, like install packages in Salt state. But it can also render scripts and things like that too. So there's those sorts of things that we have to sign. And then once everything is signed, we can turn on full signature enforcement, and then we can work on our next project. Okay, but you know, like everything else, there's deployment reality. And so this is more like what things actually felt like going through the project. So you know, first thing we're doing is we're actually patching software, which like is not ideal. This means, okay, well now you got to make sure patches apply on new versions when there's updates, and you're having to deal with that. So patch delta is not fun. Ideally, we're contributing it back, and we're using tools that are well supported. Now that we're injecting ourselves into the build system, now when there's a problem, people come to us and say, hey, why is this not working? What happened? What changed? Well, now we're part of that, and we have to support that. And then things like signing an entire repository of Debian software or container registries, that's a lot of processing and a lot of post-processing to inject yourself in. So that's tough. And then also if you are now signing packages and you have a new package, you have to be your own mirror. You can't just like do one repository and call it a day. And like I mentioned, it's finding all the one-offs and things like that. The last thing I think was really the biggest problem was that we couldn't actually start using IMA enforcement until everything is signed. So it was really an all or nothing problem, which was not ideal. So one of the things that we added into the kernel was creating a different mode for IMA appraise. So IMA appraise, as Fred mentioned, has log, enforce, and fix. We added a new mode called selective enforcement. And so what this allows us to do is solve that all or nothing problem by allowing us to say, well, if there is a signature, we'll verify it. But if there's no signature, we'll let you execute it and we'll log it. This is a good pragmatic way to handle the transition through assigning all the things and also being able to test our stuff and test verification at the scale that we have. And if you're interested, we posted the patches as well. You can go to the URL here or scan the QR code. All right, so the other problem I mentioned is, are we fully signed yet? So this is another problem in itself. And so what we did was we looked in a very convenient sysfs directory that IMA creates, which tells us for a given path, is there a signature attached to that binary or not? And so what we do is we created some ways of gathering these metrics on each of our machines and seeing, okay, for a given path, what signatures are involved. And then once we get those metrics back, we then map that path to how we think it could have been installed. And I'm going to get more detail there. So typically this is pretty easy. Path is installed at user bin foo, dpackage-s or something. We can say, oh, it's installed with lib foo or whatever. But sometimes there's symlink, sometimes there's salt states that do weird things, and we have a hard time attributing it to the original source. So we're getting better with that. But our goal is to eventually ensure that everything's signed so that we can flip on the switch that says you cannot run any unsigned software anywhere. And of course, we visualize things with Grafana to help us with that in real time. Okay, so now that we know how we're tracking progress, how does the signing and installation process work for an entire repository? So this is another project that we had to tackle, was actually just getting everything signed. And we started looking at a lot of off-the-shelf tooling first. We needed a tool that could mirror, then also run some kind of custom executable code to sign something, and then repackage that package, and then publish that to the repo. And if you all have dealt with different tooling, there's really good tools like aptly, reprepo, FTP sync, et cetera, et cetera. So we started looking into those tools. And at first we tried aptly, and we actually patched it to get this thing working. And that's nice, but again, like this is introducing now something that's not well supported, that's a bit of a fork, and that approach had a lot of pitfalls. We then looked at things like FTP sync and repro, and we noticed we're also having to make a lot of modifications, and it was kind of farther from ideal. And then we started trying to write a tool from scratch. I didn't get very far in this, but I realized, okay, this is a lot of work. I'm reinventing aptly now. Maybe I should do something better with my time. So finally, we actually just ended up using aptly, but we just separated out some of the concerns in terms of mirroring, signing, and publishing. And what we created was something called Trusted Aptly. And so what this is, it's a service that we can run that periodically runs, so it's a cron job, where it's mirroring packages from Debian. It then puts these into an unsigned repository, and then we calculate, like, okay, given the mirror that we have that's unsigned and our internal repository of signed packages, what's the diff? What do we need to add, what do we need to remove? For things that we need to add, we then can pull from our KMS or key store and use that to sign the package and put it back into our signed, or put that signed package into our signed repository. And then finally, we snapshot and publish that to our own mirror, and we use something called R2, which I'll talk about in a second, as well as publishing it to secondary mirrors. Again, now we're our own, we have to host this ourselves, and if we only have one copy of it and it goes down, that's a bad thing. All right, so what's R2? R2 is Cloudflare's object store that you can use today, so you can, I think, sign up for a free account and use it. But it can also host apt repositories, so this is pretty cool. So it's an S3 compatible storage device, and you can use things like aptly or rclone to actually just push packages into it. And then you can, with a few clicks of a button, actually set up a custom domain where you can then point your apt sources to R2, to the URL that you specify here, and then pull packages from it. So it's really cool. And the other benefit here is like not just that it's free and it's easy to use, but also because of our global infrastructure, you're not deploying it to a single region, you're just deploying it everywhere. So whatever server you hit or wherever your user that's apt updating, they'll reach the closest replica, closest server to pull this from. Cool, but that also introduces another problem, which is we want to design everything at Cloudflare like as if it's critical infrastructure. And what I mean by critical infrastructure, I'll describe through this analogy. So how many were here in Austin in 2021? Do you remember when it got a little cold outside and the power stopped and all sorts of crazy things happened? I remember. I don't think I'll ever forget. It was really difficult and tragic, a lot of things that happened, but one of the things that I learned about and read about in more detail later was that potentially our grid could have collapsed. And if the power grid collapsed, one thing that I learned is that you actually need power to start up the power grid. You can't just like turn a switch on and be like, let's start generating power again. No, you actually have to have ways to bootstrap that and get back up into running. Well, if we're creating a mirror and it's based on our infrastructure and our infrastructure goes down, we might need a mirror to update it to fix our infrastructure. So we were potentially, if we're not thinking about this carefully, creating a similar problem where we could go down and we could not get ourselves back up. So this is why we designed our solution to have multiple mirrors and ways of backup. Cool. And then like anything else, anything we design at Cloudflare, we want to design it with the kind of engineering rigor that we normally apply. Good monitoring, incident response processes, and alerting. Okay, so what's next? We want to assign all the things. We're working through getting to complete, and every executable and script has a signature. Right now, we're also looking into containers and making sure that our containers that are running across our infrastructure are fully signed. And the last bullet point we're doing here, we're trying to share what we're doing with everybody to see if you all have better ideas or maybe some of the stuff that we're doing could be useful. So, in summary, this is, if it's executable, we want to sign it. As Fred talked about, IMA works great. IMA is a nice system as long as you can store those extended attributes somewhere. And part of our challenges is where do we put those extended attributes and how do we deliver that? And we had to do some hacking with Debian packaging. Then finally, like deploying at scale, all or nothing approaches don't really always fit the bill, especially for a large infrastructure where you want to be more pragmatic really helps. Cool, so I think I'll leave it at that and I'll say thank you. If you have any questions, feel free to ask them and our emails are here if you have something later. So thank you very much. Questions, yes?
Sorry, this is really early in your talk. If an attacker can write to a binary, can't they write to the extended attribute?
Yes, but we also have other security policies in place to prevent modifying extended attributes. You'll have to be root to modify the extended attributes, yeah?
Yeah, more or less. If you're going to be replacing the extended attributes on the file, generally speaking, for one, if you are able to replace them, you're going to give it a bad signature because our key is stored elsewhere, right? Yeah, I mean, I need to I need to retest that because now you're making me forget on stage. But yeah, I do think you kind of I think you do need to be root to actually apply them.
So.
It would also need to be root to modify the file.
Potentially, but the other thing I think that Fred's point is like you'd also have to like know a private key to sign it correctly. So if you don't sign it correctly, you fail verification.
Right, that's the whole point. You drop a binary in our system, we'll know immediately and it won't execute.
Yeah.
What are your ideas for signing containers?
Yeah, so for signing containers, I think we'll take a similar approach of kind of injecting ourselves into the Docker the registry component before users actually pull it. We want to be able to let developers push as normal. We pull it, we unpackage unarchive the whole thing, sign all the binaries, repack it, and push it into the repository. And then that becomes what people actually use.
But the cool thing is that OCI actually uses tarballs that do support extended attributes, so we won't have to do anything fancy with deploying those, I think, which is going to be great, of course.
Yep. So,
Only because you asked for suggestions, and I know this is kind of opposite. I understand that within the BSDs there is a CH flag that you can apply to files, and even root can't change them. You have to move into like a rescue mode, and then take that flag off and then move into like just
Okay.
something that stands out to me when you think that Joe's talking about moving change. But I wanted to ask, when I hear this, I basically think this is public key infrastructure for files. And do you guys also use certificates for SSH, because it just seems to me like in the same operational security.
Can we, like, I don't know, that could be a whole different talk, I think.
I mean, we have our own product for security systems.
Yeah, oh, yeah.
So yeah, we use that mostly internally.
I mean, to answer your question about the attributes thing, yeah, I mean, Linux does have it's like CHATTR or something like that, right? That you can use to deny applying like additional attributes to files. Those are fundamentally different from the security attributes themselves. Yeah, but I mean, it is possible to block root from actually adding extended attributes from like the security.ima perspective as well, because it is an LSM. You can, in theory, write policy to say, okay, well, no one past a certain point is allowed to edit the extended attribute. Yeah.
Last thing, I don't want to hog. How did you guys choose salt?
I didn't choose Salt, Salt chose me.
No
so-
comment.
We got one more, we have time for one more question? Okay, one more question.
This approach might be really good for places where you already have the executable in your file, you know what you're executing, but what about places where the tool themselves now is executable, and we're trying to accomplish time? Is that a common practice? Do you want to exclude it in the future?
Yeah, I mean, we want to verify everything, so in those cases where a tool might be downloading something, we don't want that to actually be how we're running. We want those things to be done before it gets deployed. So we want to be able to stop maybe that sort of situation from happening on a metal that's, or on a node that's actually running.
Right, but from the Salt perspective, Salt can create scripts as well. Yeah, I mean, that is something that we're kind of looking into. I don't want to divulge any details for that because that could be a security problem. I'm not sure yet, but it's something we're still looking at. I guess we'll let you know when we find out.
Yeah. Okay, cool. Well, thanks everybody for attending.